Section 3.6, Hopital's rule, indeterminate forms. All right, so we talked about indeterminate forms earlier in the semester. That's like whenever we have 0 over 0 or infinity over infinity, we can't determine what those are. Because what wins out? 0 on the bottom is undefined, 0 up top is 0, so it's a conflicting issue, or we can't determine what it is. In fact, let's look at these limits, okay? We looked at these limits earlier during the semester. As x approaches 0, the sign approaches 0, right? As x approaches 0 here, obviously that part is 0, right? But didn't we learn that this was actually equal to 1, that limit? And this limit, what happens as x approaches 2? That's 2 squared, or 4 minus 4, 0. It approaches the numerator. And the denominator also approaches 0. But this limit is indeed 4. Like if we go through and we factor and we divide out like factors, we'll get 4. All right, so we're going to learn a rule real quick for dealing with indeterminate form 0 over 0. Hopital's rule for 0 over 0. All right, now, this says a whole lot, actually. I'm not going to bore you with the details on the video, but you can look at it in notes. It says, suppose we have differentiable functions and so forth, and the limit as x approaches a of f of x is equal to 0, limit as x approaches a of g of x is equal to 0. And suppose that whenever you take the limit as x approaches a of f prime over g prime, and that limit exists, or it's infinity or negative infinity, what you can do is you could say, okay, the limit of f over g is equal to the limit of f prime over g prime, and calculate that limit instead. All right, so let's look at some examples here. Let's suppose we have find the limit. Find the limit. Find the limit. Part A. Part A, we're going to have what we just had. Limit as x approaches 0 of sine of x over x, okay? Now, let's see what happens. As x approaches 0, your numerator approaches 0. As x approaches 0, your denominator equals 0. So you have indeterminate form 0 over 0. So you have this. So basically what it says is, try to rewrite this limit as the limit of the derivative at the top over derivative at the bottom. So I'm going to try to rewrite this as the limit as x approaches 0 of the derivative at the top. What's the derivative of sine of x? Cosine of x over the derivative at the bottom, which is just 1, right? Wasn't that the same thing as the limit as x approaches 0 of cosine of x? Now I could do this if this limit right here exists, or if it's infinity or negative infinity. Well, let's see. What happens as x goes to 0? We can look at it like the cosine of 0. And what's the cosine of 0? 1. There we go. That limit is 1. How about B? B, let's look at what we had on the board just a minute ago. The limit as x approaches, what do we have up there? As x approaches 2, as x approaches 2 of x squared minus 4 over x minus 2. All right, now this Hopital's rule for 0 over 0 indeterminate form holds if x approaches some number, as x approaches infinity, as x approaches negative infinity, as x approaches from the left or from the right, okay? So let's look at what we're dealing with first of all. We're dealing with the numerator approaches 0 and the denominator approaches 0 in this one, right? So let's try Hopital's rule for 0 over 0. So we're going to say, okay, this is the limit as x approaches 2 of the derivative of the numerator, which is 2x, over the derivative of the denominator, which is 1. Now, if this limit exists, or if it's infinity or negative infinity, they'll be the same as this limit up here. Let's see, that's the limit as x approaches 2 of 2x. Oh, well, that's just 2 times 2, or what? 4. That limit did exist. Therefore, the limit of this thing is also 4. C. Part C. Let's suppose we have the limit as x approaches 0, of e to the x minus 1 in my numerator. My denominator is going to be sine of x. All right, so let's see. What happens in my denominator? What does my denominator approach as x approaches 0? That approaches 0. How about my numerator? As x approaches 0, this e to the x approaches 1, and 1 minus 1 is 0, right? So let's try L'Hopital's rule here. So let's say that's the limit as x approaches 0 of, take your derivative of your numerator. That's just e to the x. Take your derivative of your denominator. That's cosine of x. Now, if this limit exists, right here, or if it's negative or positive infinity, I can continue doing this. Well, let's see what it is. What's the limit as x approaches 0 here? 1 up top, and at the bottom, 1. That limit existed, right? Therefore, the limit of this original is 1. All right, let's take a look at what's next. What's next is going to be L'Hopital's rule for infinity over infinity, okay? L'Hopital's rule. L'Hopital's rule. L'Hopital's rule for infinity over infinity, okay? All right, so what we're going to say here is we're going to look at this like it's either infinity over infinity or negative infinity over positive infinity or positive infinity over negative infinity, just some form of infinity over infinity, okay? We're going to treat it the same exact way we treated 0 over 0, okay? What did we say? We said the limit as x approaches a, I believe is the letter we used here. Let me see. Yeah. Limit as x approaches a, f of x over g of x. We're going to try to rewrite as the limit as x approaches a f prime of x over g prime of x. Again, if this limit exists, there is infinity or negative infinity, then we could say that. All right, so let's take a look at an example here. Find the limit. Find the limit. Part A. Part A, we're going to have the limit as x approaches infinity of e to the x exponent of x over x squared. Let's look at this limit. All right, imagine evaluating this. What does e to the x go to as x goes off to infinity? That goes to infinity. How about the bottom? What does that go to as x goes to infinity? That goes to infinity as well, right? So what I'm going to try to do is use L'Hopital's rule. I'm going to say, okay, this is equal to the limit as x approaches infinity of the derivative at the top, which is e to the x, over the derivative at the bottom, which is 2x, right? Now let's see what I have. Limit as x approaches infinity here, the numerator goes to infinity, and the denominator goes to infinity, right? So hey, that's infinity over infinity. Let's try L'Hopital's rule again. So I have the limit as x approaches infinity of the derivative at the top, which is e to the x, over the derivative at the bottom, which is 2, right? Now let's see what happens. What happens as x goes to infinity at the bottom? It goes towards what? 2? How about the top? What does that go towards? Infinity. So this whole thing goes to infinity. The limit is infinity. Or you could say does not exist. Part B. Part B, we're going to have the limit as x approaches infinity of natural log of x over the cube root of x over the cube root of x. All right, let's see. What do I need to do right here? I need to figure out what's going on first, okay? As x goes to infinity, the natural log keeps getting bigger and bigger and bigger. So it goes off towards infinity. How about this part right here? What if x goes to infinity and I take the cube root of it? It doesn't matter. If it keeps getting bigger and bigger and bigger, the whole thing goes off towards infinity. So let me apply L'Hopital's rule here. So let's see, that's the limit as x approaches infinity of, what's the derivative at the top? What's the derivative of the natural log of x? 1 over x. How about the derivative at the bottom? Isn't that 1/3 x to the negative, what, 2/3? Remember how we do that? If I go off to the side and look at that as scratch work, that's the cube root of x, right? Or x to the 1/3. Now, take the derivative of that, that's 1/3 x to the negative 2/3, right? That's how I got that part. All right, so this is the limit. As x approaches infinity of 1 over x all over, let me clean this up. That's 1 over 3x to the 2/3 like that. Well, before I do anything else, let me try to clean this thing up more. In other words, let me try to multiply by the reciprocal here. So I'm going to say that's the limit as x approaches infinity of 1 over x times 3x to the 2/3 over 1. Well, let's see, that's the limit as x approaches infinity of, all right, so what can we do here? We can divide out 2/3 of these x's with 2/3 of them here, so that's x to the 1/3 we're left with. Now, if I multiply straight across, I get 3 as my numerator, and I get x to the 1/3 as my denominator. Now let's see what happens. As x goes to infinity, the top stays fixed at 3. As x goes to infinity, the bottom gets bigger and bigger and bigger. What happens if the top stays fixed and the bottom gets bigger and bigger is the whole thing goes towards 0. The whole thing goes towards 0. All right, let's look at indeterminate form 0 times infinity. Indeterminate form 0 times infinity. Well, a lot of time people want to say 0 times infinity or infinity times 0 is equal to 0. No. You might have been told that 0 times anything is 0. Well, what that person meant to say was 0 times any number is 0. This is not a number, that's a concept. 0 times infinity does not behave the same way as a number, okay? Let me show you an example, maybe that'll convince you here, okay? Let's suppose I want the limit as x approaches infinity of x times 1 over x like this, okay? If I just keep this just how it is, the x right here is going off to infinity, right? Times, and this part goes off to what? 0? But let's actually see what this limit is. Isn't it the same thing as writing a limit as x approaches infinity of x over 1 times 1 over x? In other words, putting that over 1. But what does that give me? That gives me the limit as x approaches infinity of what? 1? Well, what is that limit? That limit is just 1, right? So if we would have said 0 times infinity is 0, we would have missed it. What is it in this case? It's 1, isn't it? All right, so let's look at how we deal with infinity times 0 or 0 times infinity. So I'm going to say indeterminate form. Indeterminate form. 0 times infinity. Now this means 0 times infinity or 0 times negative infinity. Either one. Okay. Let's put this. Try to write f times g as f over 1 over g or g over 1 over f and get to form and get to 0 over 0 or infinity over infinity and apply L'Hopital's rule. And apply L'Hopital's rule. All right, let's see. Suppose we have an example and it wants us to evaluate the limit as x approaches 0 from the right of x times the natural log of x. All right, what's going on here? As x approaches 0 from the right, this part approaches 0, right? Times, what does this thing approach? Oh man, I can't remember. Think about the graph of that thing. Y'all know what the graph looks like. Y'all had to graph that in Math 109. Didn't that graph look something like this right here? Y is equal to natural log of x. Went through the point 1, 0, and it had a vertical asymptote right here at x is equal to 0, right? So what happens as we approach 0 from the right hand side? My graph is going what? Towards negative infinity. So I have 0 times negative infinity. 0 times negative infinity. That's this case right here, right? 0 times some form of infinity. So what are we going to do? We're going to try to rewrite that as a fraction is what we're going to try to do. So let's see, we're going to have the limit as x approaches 0 from the right. And the easiest way to rewrite this as a fraction is keep natural log up top and then write 1 over x down below. Now make sure that makes sense in your head. What if I take this and I multiply by the reciprocal? Will I get back what I started with? Yes. All right, so let's see what happens. As x approaches 0 from the right, the natural log of x approaches 0, y'all told me. How about as x approaches 0 from the right here? What happens? What happens if the top stays fixed? Hold on. I just told y'all that's negative infinity. So what happens is x goes to, as x approaches 0 from the right of natural log of x. That goes to negative infinity, not 0. What happens as x approaches 0 of 1 over x? That goes towards infinity, right? All right, so I have infinity over infinity basically. So let me apply L'Hopital's rule now. So I'm going to apply L'Hopital's rule, say this is the limit as x approaches 0 from the right. Take your derivative of your numerator. That's 1 over x over the derivative of your denominator. What is that? Negative 1 over x squared. If you need to, take the derivative on the side. Do scratch work. All right, now let's clean this up. Let's multiply by the reciprocal here. So that's going to give us the limit as x approaches 0 from the right of 1 over x times negative x squared over 1. Well, this divides out with one of these. And what am I left with? The limit as x approaches 0 from the right of negative x. What What happens if I evaluate that as 0 and get what? 0. Let's look at part B. Part B, I want to evaluate. And for part B, I'm going to have the limit as x approaches infinity of x times the sine of pi over x, like this. All right, let's see what's going on here. As x approaches infinity, this part goes to infinity, times, how about as x approaches infinity here? The argument here will go to what? 0. Remember, at the top is fixed, which is about 3.14. And the bottom gets bigger and bigger. The whole thing right here goes to 0. Then the sine of 0 is what? 0. So I have the case 0 times infinity. So what do? I try to rewrite this as a fraction. So I'm going to say the limit as x approaches infinity of sine of pi over x over 1 over x. Make sure that makes sense. If I multiply by the reciprocal, do I get back at that? Yes. All right, let's see what we got going on now. As x approaches infinity, this argument approaches 0. Sine of 0 is 0. So the numerator goes towards 0. What does my denominator go to now? 0. So if I have 0 over 0, I'm going to use L'Hopital's rule now. I'm going to say, okay, this is the limit as x approaches infinity of, take the derivative of this. What's the derivative of sine? Cosine. Well, that's an outside, that's an inside, so I have to use the chain rule. So derivative of the outside at the inside times the derivative of the inside. How about the bottom? Take the derivative of the bottom. That's negative 1 over x squared. Well, let's see. That's going to give me the limit as x approaches infinity of, up top, I have cosine of pi x times, how about this derivative? What would that be? That's going to be negative pi over x squared, like that. And this is negative 1 over x squared, we said, right? Well, that's the limit as x approaches infinity of, I have cosine of pi over x times negative pi over x squared up top, right? Well, let's do this. Let's do a rewrite of this. Let's multiply by the reciprocal. So I'm going to say times negative x squared over 1. Oh, what happens here and here? These x squares divide out, right? So I'm left with the limit as x approaches infinity of cosine of pi over x. Negative times a negative gives me a positive, so times pi, right? Or I could put pi right here, it doesn't really matter. Now let's see what happens right here when we try to evaluate that limit. What does pi go to? Pi stays at pi, right? How about this? What happens as x approaches infinity? This argument goes to 0. Cosine of 0 is what? 1. So this gives me pi. For that whole limit right there is pi. All right, so let's see. Let's big picture what we did here, okay? If we have 0 over 0, try L'Hopital's rule. If we're taking a limit, we have infinity over infinity, try L'Hopital's rule. If we have 0 times infinity, try to rewrite as a fraction and get it to 0 over 0 or infinity over infinity. All right, so this is all that's going to be for Thursday's lecture, and then we're going to take back up with the rest of section, what is this, 3.6, and we'll finish that up next week.